This is the second of 2 lectures on periodic trends, and this one will cover the periodic trends of ionization energy, electron affinity, and electronegativity. I'm going to talk about ionization energy first. So first of all, just so that you understand what it is, ionization energy is the energy required to remove an electron from an atom. It is an endothermic process always, which means, of course, that it requires energy to remove an electron. It is always the valence electron that is removed first, simply because valence electrons are the easiest to remove. They're the least tightly held by the nucleus and require the lowest energy to remove. So when we talk about ionization energy, we're generally energy to remove a valence electron. All right, so hopefully you remember what effective nuclear charge is from the last lecture on periodic trends. If not, you'll probably want to review that definition. But effective nuclear charge is basically how tightly an electron is held by the nucleus. How strong of an attraction. All right, I think our little bark fest is done. So effective nuclear charge, again, is how tightly an electron is held or how attracted it is to the nucleus. And so the larger the effective nuclear charge, the stronger the attraction between the electron and nucleus, the more energy it will take to remove an electron. So you can really explain all of the trends we're getting ready to talk about in ionization energy if you understand effective nuclear charge. So the first ionization energy, that's just energy to remove one electron, decreases going from top to bottom down a group. It decreases. What does that mean? It means it gets easier to remove an electron from an element as you go down a group. Why might that be? Well, valence electrons get farther and farther away from the nucleus as you go down a group. If you remember, with every step down a group on the periodic table, we're gaining an energy level. Okay, so energy level 1 has 1 ring, energy level 2 has 2, energy level 3 has 3 rings. Okay, so clearly the electrons, as we go farther down a group, clearly the electrons, the valence electrons, get farther and farther away from the nucleus, feel less of an attraction to the nucleus, and are much easier to remove. I always give the analogy of a mother duck with her ducklings. Which duckling is going to be easier to snatch or kidnap? It's going to be the one that's farthest away from the mommy. Same thing with an electron. So as far as going across a period, left to right across one energy level, ionization energy increases. In other words, it gets harder and harder to remove an electron going from left to right across a period. So again, you need to be able to explain why, and we can explain again in terms of effective nuclear charge. What happens to the effective nuclear charge, Zeph, as we go left to right across the period? What are we doing going left to right? We're adding protons. That means we're increasing the effective nuclear charge going left to right. And so the electrons are held more tightly and ionization energy goes up. This is a very common chart when trying to show the trends of ionization energy and the other properties, and so you really need to be able to interpret this chart. So this chart is about ionization energies of the different elements. So look along the y-axis, it is the energy, ionization energy, and along the x-axis is atomic number. I can't reach it with my pen there. And so we've basically plotted all of the elements along with their ionization energy. There are clearly trends here. So let's look at the first 2 elements, atomic number 1 and atomic number 2. So these 2 represent period 1 on the periodic table. So as we said in the last slide, ionization energy increases going left to right on a period. Now this can play with your mind, because hydrogen to helium represents going left to right on the periodic table, but in this graph it's going straight up. So it can kind of mess with your mind. Element 3, lithium, starts period 2. So you can see that lithium has quite a low ionization energy, but then as you move your way from lithium to neon, that's going across period 2, the ionization energy definitely increases. So that goes along with what we said in the last slide. The ionization energy increases in general as you go left to right across the period. How do we look at the trend of going down a group on the periodic table? Well, let's pick a group. Let's just pick noble gases. So we've got helium, neon, argon, krypton, and xenon. What kind of trend do we see here for ionization energy going down a group? Well, ionization energy going down a group decreases. Okay, that fits too with what we said. It gets easier to remove an electron as the atom gets larger and larger because the valence electrons are farther away from the nucleus. All right, so if we combine the two trends that I just told you for ionization energy, and the two trends were ionization energy increases going left to right across the period, and increases going up. We were saying decreases going down, but it's the same thing to say increases going up. So in other words, these are the two directions that ionization energy increases. And so if we want to just draw like a composite line, we could draw a diagonal line. So the elements in the lower left-hand corner of the periodic table have the lowest ionization energies, and those in the upper right-hand part of the periodic table have the highest ionization energies. All right, there are a few exceptions. You may have noticed on the graph before, the ionization energy, rather than being a smooth linear relationship, goes up and down, etc. So these elements that fall off the expected trend line are what we call anomalies, or have slightly unexpected ionization energy values. All right, there are some exceptions or anomalies in ionization energies. You may have noticed when I showed you the trend where we plotted ionization energy versus atomic number, that instead of a straight line, the ionization energy kind of zigzags. And that's because there are several exceptions or anomalies, unexpected values. And so here are some examples I'm going to show you. Let's compare beryllium and boron. Okay, they are both in energy level 2. And see, beryllium is atomic number 4. Boron is atomic number 5. Okay, so they're both in the second energy level or second period of the periodic table. But beryllium's ionization energy is higher than we expect. Okay, it's up here, a peak above the line. And boron's ionization energy, strangely enough, is easier or lower than we expect. So that accounts for the jig-jag. So if you look at the electron configuration, you can kind of see how that would happen. If you remove a valence electron from beryllium, you're breaking up a full sublevel, the full 2s sublevel. And you may remember from the last chapter, it's very stable, very energetically favorable to have a half full sublevel or a completely full sublevel. So beryllium requires a little bit extra energy. Boron, on the other hand, has this lone valence electron, and so it's much easier to remove that, because by removing that single 2p electron, we're left with a full 2s sublevel. Another example of an anomaly is comparing nitrogen and oxygen. Similar reasoning that we just went through. And both of these are also in the second energy level. Nitrogen has atomic number 7 and oxygen is atomic number 8. And so take a look at them. I bet you can predict which one has the lower ionization energy. It turns out that, again, there's a special stability to this half-full sublevel, and so it's very difficult, or not very difficult, but it's more difficult than expected to remove a valence electron from nitrogen, and therefore nitrogen has an unusually high ionization energy. On the other hand, oxygen has an unexpectedly low ionization energy because by removing one of its valence electrons, it leaves it with a half-full sublevel. So if you hear weird noises in the background, like heavy breathing and growling, my dogs are having a play fight in the background. So here's a summary of the exceptions that I was talking about. You would predict, according to the trend I told you, that ionization energy gradually increases as you go left to right across a period. And although the trend is definitely in that direction, it's quite erratic. It goes up, down, up, down. Okay, so it's kind of jagged. And so the exceptions we were talking about, beryllium requiring a little bit extra energy to remove the electron, boron requiring a little bit less, nitrogen requiring a little bit more than expected, and oxygen requiring a little bit less than expected. So that's why when you see a plot of ionization energy, it's jagged. All right, when we talk about second or third ionization energies, that just means removing the second valence electron and then the third valence electron, etc. And so there's some important information to be garnered there, because depending on how many valence electrons an element has, you can get real huge jumps in the energy required to remove a certain electron once you've removed all the valence electrons. So that's kind of hard for me to word. So let me give you an example. Look at sodium, for example. Sodium only has one valence electron. It's in group 1A. And so to remove that one valence electron requires 496 kilojoules. Look the energy that is required to remove the second electron from sodium. It's huge. It's almost 10 times the energy required to remove the first one. And that's because what happens when we do remove the first electron from sodium? We are left with a very stable ion with a full outer shell. And so sodium ion says, no way, I'm not giving up another electron. I've always wanted to be noble gas-like, and now I am. So it really resists that. Magnesium, for comparison, has two valence electrons. And so the energy required to remove each of the first two valence electrons are about equal to each other. The first one's around 700 kilojoules, and removing the second one, you do the difference in energies here, is around 700 kilojoules. But look what happens when we try to remove a third electron from magnesium. Again, it's almost 10 times more energy than to remove the first two electrons. And again, that is because after removing two electrons, magnesium is now isoelectronic. I'll use big words here. Isoelectronic with a noble gas, which means it has a full outer shell, 8 valence electrons, very stable, and it's not about ready to give up another. So you'll see this type of trend. Low energy is required to remove valence electrons. As soon as all the valence electrons are gone, there'll be a huge jump. And that's one good way to identify what type of element you're dealing with. All right, so you can see that in another graphical form here. For sodium, and as a matter of fact, all elements in group 1A, they just have one valence electron, so there's one ionization energy that's quite low and then a huge jump. For all elements in group 2A, there are two ionization energies that are quite low, and then the huge jump. Aluminum, there are 3 ionization energies that are quite low, and then the huge jump. Makes a perfect multiple choice question, by the way, if I were to give you a chart like this without telling you what these elements are and then asking you to identify what group they are based on when they have the huge jump in ionization energy. So take a minute, make sure you understand how to interpret this graph. Alright, onward to the next trend. So let's see, in the last video we talked about atomic and ionic size. In this video so far we've talked about ionization energy. So electron affinity is really the opposite of ionization energy. It is when an atom gains an extra electron. Okay, so that would be like fluorine, because fluorine likes electrons, so I'll use it as an example. It's like making the fluoride ion, giving it an extra electron. The opposite of ionization energy required energy to remove an electron. Energy is usually released when a neutral atom gains an electron. Not always, but usually. So because energy is released, electron affinity is usually exothermic. Occasionally it's endothermic. Occasionally you have an atom that does not want an extra electron. For example, way over on the left side of the periodic table, group 1A, group 2A, where they only have 1 or 2 valence electrons. They're like, no, we're trying to get rid of the ones we have. We don't want another one. So they tend to have endothermic electron affinities. So electron affinities in general have a negative sign because they're exothermic. And so the larger the negative sign, or the larger the value with a negative sign, the larger the electron affinity. Alrighty, so some of the trends in electron affinity, and when we talk about trends, we always talk about the periodic table and the trend going across a period and up and down a group. So electron affinity is a little bit vague. A lot of times people don't even discuss it as a trend because it's not as distinctive as a trend as ionization energy and atomic size and electronegativity. So in general, some groups, in particular the alkali metals, group 1A, will decrease in electron affinity as you go down the column. Okay? In other words, the elements at the bottom of the periodic table are less likely to want to accept an extra electron. Okay? And that makes sense in effect from terms of effective nuclear charge again, because what are these atoms down at the bottom of the table? What do they look like as far as a Bohr model? They have lots of energy rings or energy levels around them. So the so the valence electron in an element down at the bottom of the periodic table is really going to be quite far away from the nucleus. It's not going to feel much attraction to it. So if there's another electron wandering around outside of this element, it's not going to feel a strong draw to join that element. Okay, the highest electron affinity of any group are the halogens. As you can imagine, halogens are very close to becoming a noble gas. They're right next to it. And so by gaining just one electron, they become isoelectronic with a noble gas, and they're quite stable. And so halogens do have very high electron affinity. Let's see, so the halides are isoelectronic with a noble gas. All right, so I don't even really want to draw the arrows when I'm talking about electron affinities. In general, electron affinity increases going left to right, and in general, it decreases going down. But there are so many anomalies that I don't even really want to draw an arrow here. All right, last periodic trend, electronegativity. Electronegativity is really important. That is a property we use a lot when we talk about chemical bonding, and it determines what type of bond is made, so it's a really important one. Basically, electronegativity is the tendency for an atom to attract bonding electrons to itself. So if you have two hydrogen atoms and they each have one valence electron, well, one electron period, it is this attraction for another atom's electrons that describes electronegativity. The trends are pretty clear in electronegativity. If we're looking at the periodic table, as you go down a group, electronegativity decreases. So I'm not sure if you've noticed or if you remember what it was for ionization energy, but the trends for ionization energy and electronegativity, so I'm going to just abbreviate them, ionization energy and electronegativity have the same trends, okay? They both decrease going from top to bottom down a group, and as you'll see in the next page, they both increase going. Okay, so again, just to reiterate, as you move across a period from left to right, electronegativity increases. Okay, that means that elements towards the right-hand side of the periodic table have a very high electronegativity. That means they strongly attract electrons from another atom. That can be explained in terms of effective nuclear charge because, of course, as you're going left to right across a period, you're increasing the number of protons. So there's a higher attraction for that atom in the nucleus, and it attracts other electrons. It's exactly. All right, so I want to give you an idea of the numbers, but I'll draw the arrows in too. Linus Pauling was a scientist not too long ago, actually I think it's like 1950s, but came up with a scale he called the Electronegativity Scale because they saw there was such a good correlation between the type of chemical bond an element would make and its electronegativity. But as you can see here, fluorine is the highest electronegative, has the highest electronegativity. Okay, it is the most electronegative element on the periodic table. I'd like you to also notice that group 8A is completely gone. The electronegativities of the noble gases are zero. They have essentially no attraction for extra electrons from another element. They're happy because they have the full outer shell. All right, so if I were to draw the trends in, electronegativity increases left to right across the period and decreases going down the group. Make sure when you turn this off that you can actually reproduce the trends that I've told you and that you can explain each one of them. All right, so we're about done with periodic trends. I'm going to show you all the trends together in one periodic table, and I recommend you sketch it and commit it to memory. And also be prepared, you might want to jot a little notes by each of the trends to explain the trend in terms of effective nuclear charge or size of an atom. But I want to point out before I show you that combined graph that electronegativity is related to ionization energy. When one goes up, the other one goes up. When one goes down, the other one goes down. Okay, so whatever the trend is for electronegativity is the same trend for ionization energy. So just remember those two go together. All right. All right, so here's the combined periodic table showing all of the trends. So as I said, you can see ionization energy and electronegativity have the same trends. Okay, they both increase going left to right across the periodic table, and they both increase going from bottom to top. It would be perfectly fine to write an arrow pointing down and say decrease too. They say the same thing. We didn't really go over metallic character. If you ever see, that's just, the metals are obviously located on the left-hand side of the table. So obviously you're going to have more metallic character going to the left. Okay, atomic radius is always the opposite of what ionization energy and electronegativity are. So just if you remember what direction they're pointing, point atomic radius in the opposite direction. Electron affinity, which I hesitate to even show arrows because there's so many anomalies or exceptions in the trends, but electron affinity does go along with ionization and electronegativity. It's really atomic radius that is the odd man out. That is it. So now you just need to study for your test on Thursday.